The year is 1986. Space Shuttle Challenger stands tall on Launch Pad 39B at Kennedy Space Center. It's a potent symbol of American ingenuity and ambition. On board are 7 astronauts, including Krista McAuliffe, the first teacher in space, poised to inspire the country. In reality, a catastrophic O-ring failure just 73 seconds after liftoff led to the shuttle's explosion. That tragedy stunned the world, halted the shuttle program for years, and profoundly impacted public perception of space travel. But what if that disaster was averted? What if the fatal flaw was detected and corrected just in time? Today we delve into a world where a national tragedy became a triumph. What if the Space Shuttle Challenger mission was a complete success? Our alternate timeline begins on the bitter, cold morning of January 28, 1986. Imagine this. In the hours leading up to the launch, a diligent engineer, perhaps one who had voiced concerns about the O-rings in cold weather, insists on one final, exhaustive inspection. This time, their warnings are heeded. The anomaly is found. The launch is scrubbed at the last minute. The problem is identified, rectified, and Challenger launches successfully a few weeks later, perhaps on a warmer day. The immediate impact? A wave of national relief. Soaring pride quickly follows. Krista McAuliffe becomes the first teacher in space, inspiring millions of students and sparking a renewed passion for science and exploration across America. The mission is a resounding success, demonstrating the shuttle's reliability and extending NASA's public goodwill. Krista McAuliffe's successful mission, instead of ending in tragedy, marked the beginning of an extraordinary public career. She returned to Earth not as a posthumous symbol, but as a vibrant, articulate, and incredibly effective advocate for education and science. Her experiences in orbit, vividly recounted in classrooms, auditoriums, and television specials, brought the abstract wonders of space down to Earth. She became a household name, synonymous with learning and exploration, her face gracing magazine covers and inspiring countless school projects. Her ability to connect the vastness of space to the everyday curriculum proved revolutionary. She didn't just teach about space, she brought space to the classroom. Her legacy would be etched into the fabric of American education. The Teacher in Space program didn't just survive, it thrived. Inspired by McAuliffe's triumph, other civilian professions were quickly invited to participate. We saw a journalist in space, offering unprecedented live reporting from orbit, transforming news coverage and public engagement with space. Imagine nightly news segments featuring a correspondent floating effortlessly, describing the curvature of the Earth or the daily life aboard the growing space station. This made space exploration an immediate, visceral experience for millions. An artist in space might have created unique zero-gravity sculptures or paintings, pushing the boundaries of human creativity and introducing a new dimension to contemporary art. Their works, displayed globally, would fetch astronomical prices and inspire art forms yet unimagined. Later, perhaps a physician in space conducted groundbreaking medical observations firsthand, or an engineer in space personally tested new construction techniques for orbital habitats, streaming the process live to university lecture halls. These missions weren't just symbolic, they generated real-time educational content, interactive lessons, and scientific data that was immediately integrated into curricula across the nation, making STEM education hands-on and exciting. This democratization of space travel profoundly transformed public perception. Space became less of a distant, dangerous frontier for a select few, and more of an accessible realm for human endeavor and ingenuity. The continuous narrative of success, coupled with the relatable stories of civilian astronauts, fostered a deeper connection between society and the cosmos. Public opinion polls consistently showed strong support for NASA's budget, often citing the direct inspiration and educational outreach stemming from these civilian flights. The sheer number of students entering STEM fields soared, driven by a generation that had seen their own teachers, journalists, and artists reach for the stars. Universities reported record enrollments in aerospace engineering, astrophysics, and material sciences, fueling a robust pipeline of talent. Science museums saw attendance boom, And even popular culture, from television shows to films, embraced a more optimistic vision of humanity's future among the stars. The space program was no longer a Cold War race, but a shared human adventure, with America leading the charge. This cultural shift extended beyond the classroom. It permeated public discourse, fostering a belief in American exceptionalism and the boundless potential of human ingenuity. Innovations stemming from space technology were lauded, and the public looked forward to every new announcement from NASA, eager to witness the next step in humanity's cosmic journey. The commercialization of space also accelerates dramatically. With perceived reliability, private companies are more willing to invest. Space tourism, once a fringe concept, begins taking tentative steps towards reality by the mid-2000s, perhaps with suborbital flights becoming a luxury for the ultra-wealthy, and dedicated modules on the ISS being leased for private research or even short stays. This vibrant new industry, while still nascent, further cements space travel in the public consciousness as an accessible, albeit expensive, frontier, attracting a new wave of entrepreneurs and investors. The sheer scale of the vision captivated venture capitalists, leading to the rapid development of new launch providers and space-based services. Entire new industries emerged, from asteroid mining prospecting companies to orbital manufacturing startups, all fueled by the seemingly boundless success of the shuttle program. The political and technological consequences were immense. Instead of years of grounded flights and intense scrutiny following a disaster, the shuttle program maintained its ambitious launch schedule. This uninterrupted cadence directly accelerated the construction of the International Space Station. In our timeline, the ISS struggled with delays and budgetary challenges. Here, with a reliable shuttle and consistent public support, its modular components were delivered and assembled at a breathtaking pace. We might see the ISS fully operational by the late 1990s, perhaps even a year or two before the turn of the millennium, years ahead of its actual completion in the early 2000s. The station, a permanent beacon in the night sky, became a global symbol of scientific collaboration and human achievement, a testament to what humanity could achieve when united by a common goal. This early completion wasn't just a matter of national pride, it was a scientific revolution with tangible earthly returns. A continuously crewed, fully equipped orbiting laboratory operating for an extended period allowed for unprecedented, long-duration microgravity research. This directly translated into accelerated breakthroughs in several key areas. Advanced material science. Early and sustained microgravity experiments in crystal growth led to the development of novel, ultra-pure semiconductor materials far sooner. Imagine microprocessors with significantly higher clock speeds and lower power consumption by the late 90s, boosting the nascent internet and personal computing revolution. These superior chips accelerate the development of early smartphones and sophisticated gaming consoles. New alloys, stronger, lighter, and more heat-resistant than anything developed on Earth, revolutionized aircraft design and automotive engineering. This led to more fuel-efficient vehicles, significantly reducing reliance on fossil fuels, and safer, more resilient structures in construction. Space-grown optical fibers, free from gravitational imperfections, enabled faster, clearer data transmission for a booming telecommunications industry, paving the way for broadband internet access much earlier than in our timeline, potentially shaping the digital landscape of the early 21st century in unforeseen ways. The impact on satellite communications was also profound, enabling global connectivity at speeds previously unimaginable, shrinking the world further and fostering greater economic interconnectedness. Biotechnology and medicine. Understanding human physiology and prolonged microgravity advanced rapidly. Early insights into bone density loss, muscle atrophy, and cardiovascular changes led to more effective countermeasures for astronauts, but crucially, also provided data for treating osteoporosis, sarcopenia, and heart conditions on Earth. Pharmaceutical companies quickly recognized the potential of protein crystallization in space, unimpeded by gravity, to yield purer protein structures. This accelerated drug discovery for a range of diseases, from AIDS, which was ravaging populations in the 80s and 90s, to various cancers and autoimmune disorders, potentially bringing life-saving treatments to market years earlier. We might even see earlier successes in tissue engineering or organ printing technologies, benefiting from microgravity's unique environment, leading to advancements in regenerative medicine. The ability to perform long-term biological studies in space also offered new perspectives on aging and disease progression, potentially extending healthy human lifespans. This accelerated medical progress wouldn't just be theoretical. It would directly impact public health and quality of life globally, potentially adding years to average human lifespans in developed nations and offering hope in regions suffering from chronic diseases. Combustion and fluid dynamics. Experiments on how flames behave without convection and how fluids interact in zero-G led to safer and more efficient combustion engines on Earth, as well as innovations in industrial mixing processes for chemicals and advanced microfluidic devices crucial for diagnostics and analytical chemistry. Insights into fluid behavior in space also contributed to more efficient water recycling systems for future long-duration missions, a technology that found its way into drought-stricken regions globally, offering practical solutions to pressing environmental challenges. The lessons learned about contained combustion also advanced fire suppression technologies, making homes and workplaces safer, and even influencing the design of more energy-efficient industrial furnaces. Beyond the ISS, the consistent launch schedule allowed for the earlier deployment of other critical instruments. The Hubble Space Telescope, launched in our reality in 1990 after shuttle delays, could have been deployed as early as 1988 or 1989. Imagine years of groundbreaking astronomical discoveries arriving sooner, perhaps revolutionizing our understanding of dark matter, dark energy, or exoplanets well before the turn of the millennium. Early observations could have identified the first confirmed exoplanet candidates earlier, igniting the field of astrobiology and accelerating the search for extraterrestrial life. Earlier data from Hubble could have redirected research efforts, potentially leading to new theories or even more powerful space-based telescopes designed for exoplanet characterization much sooner. This accelerated pace of discovery not only expanded scientific knowledge but also captivated the public, fueling continued support for space exploration. Other vital satellites for GPS navigation, advanced weather forecasting, and environmental monitoring were also launched more swiftly, offering enhanced capabilities that subtly improve daily life, from more precise agriculture to earlier warning systems for natural disasters. The rapid accumulation of Earth observation data would also have provided a clearer, earlier picture of climate change impacts, potentially spurring earlier global action. The very act of observing our planet from above, through these advanced sensors, fostered a deeper environmental consciousness globally, perhaps leading to more proactive environmental policies and technologies, and even new international agreements, accelerating the global response to climate change by several years. The perception of American leadership in space remained unchallenged throughout the late 1980s and 1990s. This sustained success subtly shifted the geopolitical landscape. While cooperation on the ISS continued, indeed it was perhaps even more seamless given the lack of major interruptions, the sheer effectiveness and perceived reliability of the U.S. shuttle program put significant pressure on other spacefaring nations. The Soviet Union, grappling with its own profound internal economic and political challenges leading up to its dissolution, found it harder to compete on a grand scale. While their Soyuz program continued its reliable service, the spectacle and scientific output of the shuttle ISS complex created an undeniable prestige gap. This might have altered the dynamics of the nascent post-Cold War space cooperation, perhaps leading to a less equal partnership where the US dictated more terms, or conversely, a greater push for the Soviets to find cheaper, more innovative ways to stay relevant. After the fall of the USSR, the newly formed Russian Federal Space Agency might have found itself in an even more subordinate position, relying more heavily on U.S. contracts for ISS crew transport rather than developing competitive launch capabilities. Their economic struggles would have been more pronounced without the bargaining chip of being the sole provider of human access to orbit for a time, as they were in our timeline. This dependence could have led to greater resentment, or conversely, a deeper integration into a US-led space order, fostering a new kind of space diplomacy where Russia's primary role was as a key but junior partner. Meanwhile, nations like Japan and the European Space Agency ESA, with their own ambitious space programs, watched with a mix of admiration and heightened determination. Japan might have accelerated its H-2 rocket development and modular space station components to demonstrate independent capabilities, pushing for more ambitious robotic lunar missions and even early asteroid sample returns, perhaps to secure valuable off-world resources. ESA, driven by the desire to not be left behind, might have invested even more heavily in its Ariane launch family and robotic planetary probes, perhaps even pushing for an independent European human spaceflight program sooner, or at least a more assertive role in ISS operations beyond mere module contributions. This could have led to a stronger, more independent European space program much earlier, possibly launching its own advanced orbital vehicles in the early 2000s, leading to a truly multipolar space landscape for robotic exploration. China, still in the nascent stages of its manned space program, would have watched with a keen strategic eye. The continuous American success would have been a powerful motivator, potentially accelerating their own Shenzhou program and long-term goals for a Tiangong space station and lunar ambitions, driven by a desire to demonstrate their own technological prowess on the global stage. This could have set the stage for a more pronounced new space race in the 21st century, albeit one less tied to Cold War ideologies and more focused on economic and technological prestige. The competition for resources and influence on the Moon and Mars could intensify, perhaps leading to new international treaties or, conversely, escalating tensions over off-world territories as nations stake claims. Fueled by constant success, talks began in earnest about manned missions to Mars. No longer a distant, abstract goal, it became the logical next step for humanity. Public excitement, consistently stoked by shuttle triumphs and the civilian astronaut program, ensured strong political will and sustained funding. Initial concepts for a lunar gateway, not just for future Mars missions, but as a stepping stone for renewed lunar exploration and potentially even lunar resource extraction, gained traction. Perhaps robotic missions, focused on prospecting for water ice at the lunar poles, were launched even earlier than in our timeline, laying the groundwork for future lunar bases or in-situ resource utilization. Detailed plans for the Red Planet Direct mission architecture, or similar ambitious proposals, might have entered serious development by the late 1990s, aiming for a human landing on Mars by the late 2000s or early 2010s, a full decade ahead of our current projections. The very audacity of the goal seemed eminently achievable in this era of unbroken space success, pushing the boundaries of what was thought possible for humanity. Committees were formed, international partnerships explored, and a palpable sense of excitement permeated the space community and the public alike. The idea of humanity becoming a multiplanetary species gained mainstream acceptance much earlier, shaping scientific education and career aspirations across the globe. This era would be defined by the image of Mars or bust, with entire industries pivoting to support the monumental challenge of interplanetary travel, from advanced propulsion systems to closed-loop life support and long-duration habitability. The excitement was almost palpable. A new golden age of space exploration seemed to be dawning. However, this alternate reality isn't without its deeper, more insidious potential drawbacks. The very success and perceived safety of the shuttle program could lead to a dangerous overconfidence within NASA. Without the jarring wake-up call of the Challenger catastrophe, a disaster that in our reality forced a painful, top-to-bottom reevaluation of safety protocols, management structures, and the very culture of risk, the hard lessons learned might never be fully internalized. The stark contrast between the pre-Challenger era's hubris and the post-Challenger commitment to safety would simply not exist. This absence of a catastrophic failure fosters a subtle, creeping phenomenon known as the normalization of deviance. Small anomalies, minor technical glitches, or deviations from established safety procedures that, in isolation, don't cause immediate harm, slowly become accepted as just how things are done. Engineers might flag a recurring issue, like excessive vibration on a particular engine during ascent, but if the mission completes successfully, the concern gets downgraded from a critical flaw to a known anomaly to monitor. This subtle shift in perception was insidious. The pressure to maintain the ambitious launch schedule, to meet political deadlines, and to sustain public enthusiasm might subtly override engineering concerns. Whistleblowers, if they emerged, and there likely would be some given the inherent risks of spaceflight, might find it harder to be heard. Their concerns are dismissed as overly cautious, overly pessimistic, or even disloyal in the face of continuous success. If it ain't broke, don't fix it, becomes the silent mantra, even when the it is showing minor, intermittent signs of stress. Budget cuts, justified by the program's flawless record and perceived robustness, could be pushed through without sufficient oversight, incrementally eroding safety margins in areas like maintenance, inspections, and quality control. This isn't a sudden, dramatic breakdown, but a slow, almost imperceptible drift towards a less rigorous environment where risk is unconsciously redefined downwards and critical questioning is inadvertently stifled. The institutional memory of how close Challenger came to disaster simply doesn't exist, leading to a dangerous amnesia regarding past warnings. The silence of unbroken success becomes deafening, preventing the very introspection necessary for true long-term safety. This unaddressed cultural and systemic rot could set the stage for a different, perhaps even larger tragedy further down the line. Fundamental design flaws or operational risks, which were meticulously investigated and rectified after both the Challenger and later Columbia disasters in our timeline, might remain unaddressed. For instance, the vulnerability of the thermal protection system to foam strikes, a key factor in the Columbia accident, might never be fully recognized, let alone prioritized for a major redesign. Engineers might observe foam shedding during launches, but without a catastrophic event, it would be categorized as an acceptable flight characteristic or a known but benign anomaly that is simply managed. The focus would be on keeping the shuttle flying, not on fundamental redesigns or exploring alternative launch systems. This reliance on a perfect shuttle system could lead to technological stagnation within NASA. Instead of aggressively investing in newer, safer, and more cost-effective launch vehicles like the expendable rockets that later gained prominence in our reality, the agency might cling to the shuttle for too long, convinced of its infallibility. This could allow other spacefaring nations investing in novel propulsion or launch architectures to surpass the U.S. in key capabilities over time, despite America's initial impressive lead. The very infrastructure of space access might become reliant on an aging system, making a transition to future goals harder and potentially more perilous, even for a mission to Mars, which would demand entirely new levels of reliability and redundancy. The irony would be palpable. The path to Mars, seemingly cleared by uninterrupted success, would in fact be paved with accumulating, unrecognized risks. The butterfly effect could even manifest in human terms. The diligent engineer who saved Challenger, a hero in this timeline, might later face an agonizing ethical dilemma. Pressured by a management team now convinced of the shuttle's invincibility, they might be forced to compromise safety for speed on a future mission, perhaps for a critical component of the Mars transit vehicle or a new ISS module. This would reveal a deep tension between the pursuit of progress and the paramount importance of safety, a moral struggle that might have been averted by a painful public failure. The very success that propelled America forward might, in the long run, mask a growing vulnerability, setting the stage for a reckoning that, when it finally arrived, would be all the more devastating for being entirely unexpected. It would be a tragedy born not of a sudden failure, but of a slow, creeping erosion of vigilance, a consequence of having never been truly humbled. The public, having only witnessed triumphs, would be utterly unprepared for a sudden, devastating loss. The shockwaves would be immense, potentially even more destabilizing than Challenger was in our timeline, precisely because it would break a decades-long streak of perceived invincibility, shattering an almost mythological belief in the program's flawlessness. This hypothetical disaster, whenever it occurred, would not only ground the fleet, but also force a far more brutal introspection into a culture that had become blind to its own accumulating risks, challenging the very foundation of America's unblemished space legacy, and perhaps triggering a more profound and prolonged crisis of confidence in space exploration than anything seen in our actual history. The world would grapple with the question of whether unbroken success had made humanity soft, less vigilant, and ultimately more vulnerable, questioning the very core values of an enterprise that had been held up as a paragon of human ingenuity. In this alternate history, the world looks up to the stars with an unbroken sense of hope and progress. The Challenger mission, instead of becoming a somber cautionary tale, remains a shining example of humanity's reach for the heavens. It propels America, and indeed the world, further and faster into the space age. Yet beneath this shining facade of continuous triumph, the unspoken question lingers. What price does unchecked success truly exact? Does the absence of immediate failure inevitably breed the conditions for a greater, more insidious one in the future? And if a new tragedy were to strike in this timeline, born from a culture of hubris rather than an unforeseen technical flaw, how would a world that has only known triumph react to its first true space disaster? The answer to that could define the next chapter of this ambitious, yet potentially fragile, alternate space age, forcing humanity to confront the uncomfortable truth that even the most inspiring successes can cast the longest shadows, hiding the seeds of future downfall and demanding a vigilance that only failure sometimes provides.